So it's my pleasure to introduce today Alexander Koller from Universität of the Saarlandes. And he's a computational linguist of the European sort, meaning that he works on all kinds of wonderful theories of structure of trees and connects it up to logic. Has done a lot of work on unification formalisms and particularly underspecification, which is relevant to questions in particular of how you construct a tree if you're doing it in something other than the standard order. If you would like to be able to parse quickly by making use of the information you have before you have everything, or because you want to be able to represent ambiguity, for example, scope ambiguities in a factored way, despite the fact that at first might seem to be impossible. You'll be happy to know that he does have the requisite credential of having worked on A-star parsing, dependency parsing in fact. So is armed with statistical credentials. It's like Nixon going to China. He can tell us about all the wonderful other side and where Europe has gone since the divergence. I'm exaggerating. Anyway, a great pleasure, and Alexander Koller.
Is the divergence the War of Independence?
Yeah. Yes.
Okay. Good. Okay.
Centuries ago.
Good. So, thanks very much for giving me the chance to give a talk here. This is actually going, I'm not going to talk about statistics at all in this talk. I hope this is no disappointment for you. And there's very little logic in the talk. So what this is about is, it's work that's in my thesis, but this comes out of a joint project with a lot of other people in Saarbrücken, and this is the preliminary end result of several years of work that's been great fun for us. Okay, so what is this talk about? First of all, I'm going to tell you a little about ambiguity, and in particular scope ambiguity, and one particular way for dealing with scope ambiguity. Am I talking loudly enough? Okay, good. And in particular, one kind of scope ambiguities and one way of dealing with it, which is called underspecification. And I'm going to show you one particular way of doing scope underspecification, which is the one we've developed, and which uses something we call dominance graphs. And then I'm going to go into the fact that we're not the only people who have done scope underspecification. There have been others in Europe and in the US who have done this. And it seems that everybody who has done this has basically developed their own little formalism to do it, and there has been this vague intuition around for the past 10 years or so that they were all basically the same, but nobody ever really bothered to sit down and check what's the actual precise relationship between those formalisms. And that's the questions I'm going to begin to answer in this talk. I'm going to try to encode a formalism which is called minimal recursion semantics. This is the underspecification formalism that's used in the large-scale HBSG grammars. Into our dominance graphs, I'm going to show you that this is not trivial. The translation is trivial, but it's not always correct. But it's correct on a fragment, and I'm going to try to convince you that the fragment on which it's a clearly defined fragment, the fragment on which it is correct, is actually relevant in the sense that everything you ever need in scope underspecification falls into this fragment. And then in the end, I'm going to harvest a little and show you what we actually get from this. So, first of all, ambiguity, I suppose, is something that everybody here has at least a passing familiarity with. So, we know that natural language sentences often have more than one possible meaning or syntactic structure or whatever. And one classical example from syntax is John watched the man with a telescope, where either it's the instrument of watching or the man holds the telescope, the man who is being watched. And ambiguity is one of the great challenges for natural language processing today. I think this is also a generally accepted fact. One way to deal with this is statistics, but we are exploring a different way. So the kind of ambiguity we're looking at is scope ambiguity. That's a certain kind of semantic ambiguity, which you can see in examples like every student reads a book, which has, this is the preferred reading. Each student can read a different book. So you can write this down. You can, if you want semantic representation for this, you can say for everything that's a student, there exists a book which the student reads. And then there's this other reading which you can enforce with continuations, like namely the one that Professor wrote. And then the quantifiers are basically turned around. First, if you say there is one single book and every student reads this book, why? It's called a scope ambiguity because the main difference in between these two logical representations is that the subformula over which the quantifiers for all x and exists y take scope, that's the basic difference between those two semantic representations. And now, you can do it with, very small examples with, 2 readings, and it's completely boring. For people who have, argued for the interestingness of scope ambiguities, like Jerry Hobbs, for example, also an American, have, come up with increasingly big examples, that, this one is predicted by theory something like 600 readings. And you see it has all these little every voter and every single issue, most issues that give it this blow up. And in general you can say, ambiguity is a bad thing because if you have a number n of ambiguity sources, the number of readings in the worst case can be exponential in n. Now, this looks like a somewhat esoteric example. I mean, you do find examples like with scope ambiguities in real corpora. They don't look like this, but typically you would get things where you have adverbials or sentence embedding verbs or things like this. But you get it from completely harmless sentences too. So if you take a modern large-scale grammar like the English resource grammar, which is one of the big HBS3 grammars, and you give it this completely harmless sentence, which is from a verbmobile corpus, but that would give us all day Tuesday to be there, the grammar will predict that there are something like 65,000 readings. Of course, nobody believes that this sentence really has 65,000, distinguishable readings. Yeah? But, they made some design decisions which, when you look at them, are, not terribly stupid. I mean, because they want a uniform treatment of noun phrases in their grammar, things like that. It ends up having, to predict this kind of readings. And that's a problem. I mean, if you imagine that the sentence has a few thousand readings, because it's syntactically ambiguous, this one perhaps isn't. But if you imagine you did have a syntactically highly ambiguous sentence, and then each of the syntactic readings again has this number, or at least the grammar says it has this number of semantic readings, you have to be able to deal with these millions of readings somehow. So that's the basic problem that we want to deal with. So the setup classically is like this. You have one sentence, you have, let's say, you pick one syntactic analysis, or it's perhaps not ambiguous, but if it is, you just pick one. And then you have a big number of semantic representations, and all you can do here is you can enumerate them all, and then you're stuck with your couple of million semantic representations, and you have to perhaps pick a good one from those. But really what you want to do is not to enumerate all those, many semantic readings in the first place. What you'd like to be able to do is to avoid the enumeration for as long as you can. Is this a question?
Yeah. Are you assuming in that diagram that there's no syntactic ambiguity?
If there's syntactic ambiguity, then you just add more layers to this diagram. Yeah. So I'm not assuming that. So even that there could be more syntactic readings here. I don't care about
I just mean for purposes of the talk, you're only concerned with this last step.
Yeah. So I'm not talking about syntactic ambiguity here.
Yeah.
Syntactic ambiguity is not relevant to anything I'm going to say today. So what we'd like to do is to avoid enumerating those semantic readings. One thing, the main reason why we'd like to avoid that is because most of those readings were not intended by the speaker anyway, or perhaps they're just all equivalent, and it's really a spurious ambiguity. And it would be computationally useful if you could actually look at something else, which I'm going to call an unspecified description, and then narrow down the range of possible readings to those that are actually meant, or throw out readings that are equivalent to others in order to get rid of spurious ambiguity. And then there's also a cognitive question, and that's all I'm going to say about this, just this one bullet point. Arguably, people probably don't enumerate all those readings in their minds and then, select from them. They do something different, I don't know what, but anyway, this way of doing it is neither computationally nor cognitively a terribly good idea. Okay. So how does this work, this scope underspecification? Our goal is to avoid enumerating the readings for as long as we can. And to do that, we take a single syntactic analysis. You can do it, if you have syntactic ambiguity, you can do it for every single one, or you could do it from a parse forest or something like this. And then from this single syntactic analysis, you derive not the many semantic readings, but a single underspecified semantic representation from it. And then you can use this level of underspecified semantic representation, I call the objects on this level underspecified descriptions. And then your hope is that you can perform inferences on the underspecified descriptions in order to remove readings that were not intended by the speaker. And then if you ever, or when you need them, you can still enumerate, you want to be able to still enumerate the readings of all the readings that are represented by the underspecified description. So what you do is between the level of syntax and the level of semantics, you add another level of description, underspecified semantic representations. You get just one from each syntactic analysis, and when you need them, you can enumerate this whole set of semantic representations from this one underspecified description. Okay. So now I'm going to show you one particular way for doing this, based on what we call dominance graphs. So let's assume that the semantic representations that we're after are something, let's say for example they're formulas of first order logic, but we're not really bound to that. But let's assume for the purpose of this talk they're just formulas of first order logic. And now formulas of first order logic have a very natural tree structure. So you start with the main connective, then you put that at the root of the tree, then you take the subformula and you look at its main connective and you put that at the root of the subtree, and so on. You go through the formula recursively, and then what you can do is that you can, as an underspecified description, you can use a graph, and you can say when is a tree described by this graph? It's described if I can embed the graph into the tree in such a way that certain dominance conditions are satisfied. I'm going to show you an example on the next slide for this. You have to deal with variable binding somehow if you deal with first order logic or any logic, but I'm not going to talk about this here. This is an interesting little point, and we have ways for doing this, but that's beyond the point now. And I just like to say, so this is where some logic still comes in after all. These dominance graphs are equivalent to a logical language we call normal dominance constraints, and it's been really nice, really useful to be able to switch between the graph view and the logic view, because both sides give you nice tools for doing stuff. Okay. So just quickly, how do we translate these formulas how do we see these formulas as trees? That's the example I started with. Here are the two readings, and I've colored them suggestively. So if you look at this, both readings consist of a blue part, a red part, and the green part, and those colored parts are the same in both cases. The only difference is in the way that the red part and the green part are linked. And now you can take, for example, the second reading here and write it as a tree. So you say it's universal quantification, so you put it for all x at the root of the tree, and then the subformula has as its root an implication, so you put an implication here, and so on down all the way. And these at signs stand for application. So the student of x is application of the predicate symbol student to the variable x. Okay, so this is the tree for the second reading. This is the tree for the first reading, and now we'd like to come up with an underspecified description that actually describes these two trees at once, without duplicating things or so. And the things you can say about these trees is they consist of this red part, this green part, and this blue part. And also the green part has to somewhere as a subformula contain the blue part, and also the red part somewhere as a deep subformula has to contain the blue part. Yeah, that's true in both of these cases. Okay, so and we write this down using this dominance graph. So we say these readings consist of this red part, which looks like this, a green part which looks like this, and a blue part which looks like this. And when you embed these into a tree represents a reading of this, if you can embed all of these parts into the tree while realizing these dominance edges as reachability. So here's an example. This is the second greeting from the earlier slide. This is the dominance graph I just showed you. And now we want to say, is this tree described by this graph, yes or no? Okay, so what we have to try is to embed the parts of the graph into the tree. We can map the green stuff to the green stuff, and the red to the red, and the blue to the blue. And we can, we have to map every single node to a node over here, but we can map two nodes to the same one, so we can also map this one here. Yeah. And now it's clear that we've embedded everything. Now we have to check, have we respected these dominance requirements? And let's have a look. So it said you have to be able to go from the image of this node to this node. So let's check. That's from here to here. And yes, we can actually, there's a path in the tree from there to there. Yeah?
This looks like tag junction.
Perhaps it looks like tag junction now because I'm drawing these arrows into the same place, but it's an interesting question whether, so it has something to do with tagger junction, I think, and people have, I think, that there are dialects of tag in which they do use dominance requirements. I don't know if exactly for that purpose, but yes, people in the tag community have done sort of similar things, but I mean, used sort of similar ideas, but it's not exactly the same thing. Okay, and the same thing is of course true for this dominant edge here. Yeah, so it's realized with a path of length 0.
I must say I don't understand it. So,
okay.
What should we check here for this to be correct? What is it that we should? I mean, I'm missing.
Everything that the left inserts is true of the right thing.
So this is this graph is a representation of a set of trees. So that's what we want to use it for. Okay.
Yeah.
And
you just showed the red part, or when it included the green part.
The left, right, green, and blue parts.
So
the ones connected by those dots.
Yes.
Yes. And what did we?
So this describes a set of trees, and a tree is in this set that's described by this graph. If I can embed these subgraphs that are connected by solid edges into the tree, yeah. So I have a mapping from the nodes of the graph into the nodes of the tree. That's I've indicated some of the mappings by the dotted arrows here. That's condition number 1, and condition number 2 is whenever I have a dotted edge here from a node to another node, I have to be able to walk here in the tree from this node to that node. Yeah? So from this node to that node, there's a dominance edge in the graph. This node is mapped to this one. This blue root is mapped to this one. And yes, there's a path here. Yeah? So that's why this is one of the trees that's described by this graph. Okay, I'll show you one that's not described by it later. Okay.
So let me clarify. So,
yes.
So the green part of the tree, it says that some assertion about, in other words, for some y, the blue assertion should be true. Is that what the dotted line means? It may be true for every book. It may be true for some y or every y.
So on this level, it doesn't. So this relation between the tree and the graph doesn't really care about that these symbols have any meaning. So this is just
topologically saying it.
Yeah, it just says, there's a symbol exists y, there's a symbol at,
okay, so I should
etc.
interpret the symbol.
Yeah, and then when you're on this level of trees, you can say, oh look, this tree is actually an encoding of a first order formula, and then you can interpret it. So it's really a two-level interpretation thing, if you like.
This simply as does a
think of them as
directed graph as a tree.
Yeah, it's a directed graph in a tree, and that's all there is to. Yeah, sorry. It's a directed graph in a tree, and that's all there is to it at this level. Yeah, and then in a second step, of course, this tree is intended as an encoding of a first order formula, and then of course you can interpret it as a formula again. Yeah, but at this level, the only meaning of this dotted edge is in the tree that I map this into. I have to be able to walk from the image of that node to the image of that node. Yeah? That's all it says. Going down, yes. So yeah.
So the dotted lines are actually pointing.
Yeah, all the lines are, yeah.
So one way of thinking about this is, yeah, that's right.
So on the left, the assertion is you said this a little while ago, that the blue phrase is embedded underneath that node of the green one and embedded underneath that
Exactly.
node of the red one, and that's all that's said on the left. And what the left doesn't say is whether the red is embedded under the green or vice versa.
Yes.
And on the right, that ambiguity is resolved in favor of having red embedded under green, but that's
Exactly.
only one of the two possibilities.
Right, that's only one of the two possibilities. The other one is on the next slide.
Is it much?
The left one.
Yeah.
Is it much of a problem that you can't always tightly express the set of trees? Like if you have 3 of these things, and either 1, 2, 3 is okay, or 3, 2, 1, but nothing else. You
Yeah,
can't
there are
express-
limits to the things you can say with this, but so far we haven't really found examples in natural language where we needed this extra expressive power. Okay. So just to show you the other reading, yeah. So this was the one of them. This is the other one of them, and again you can you can find a mapping from the nodes, and which respects the dominances. So this time, this path from this requirement that you can walk from the image of this node to the image of that node is realized by a path of length 0, and the other one that you can walk from the image of this node to the image of that node is realized by this path.
So unlike some of the underspecified representations used in parsing, you're assuming not only that every node on the left corresponds to a node on the right, but also every node on the right corresponds to at least one node on the left.
Not at this point, but I'll get to that in 2 slides. That's a very, very, very important point. Okay, so here's an example of something that's not a solution of this. Yeah, so this is a tree that's not described by that graph, because yes, of course, you can embed things in the obvious way, but this over here says you have to be able to walk from the image of that green node to the image of that blue root, and there's no path from here to here in the tree. Yeah? So this is again a directed tree and has this root, so you cannot go down over edges, from this node to that node. So that's not in the set of trees that's described by this graph. Yeah? This, however, is in the set of trees that's described by this graph, so you can have extra stuff. You can say, this is perfectly good, according to the definition I just gave you. You can embed this stuff. You can have this mapping I have indicated here, and it says over here I have to be able to walk from the image of that to the image of that, and yes, I can do that. And also I can walk from the green hole there to the blue root, and I can do that again. There's other stuff in this tree, but we're not talking about this stuff, and this is, the definition allows this. Yeah. So there's a difference here between a solution, which is a tree into which I can embed the graph while respecting the dominance edges, and a configuration is a special solution which has this additional property that all the labeled nodes in the all the nodes in the tree were already present in the graph. Yeah? So this is not a configuration because there's no node in the graph that maps to this, but this is one because everything that's on the right here is also on the left. Okay? Good. So this is an important distinction to keep in mind, and I'll get back to this. So configurations are special small solutions. Okay. Now this is one way of doing underspecification. There are lots of others. And that's a bit of a problem because, on the positive side, underspecified descriptions in many of these formalisms look very similar to each other. They always have these sort of graphs, and then, it has something to do with outscoping or dominance or something like this. But a question that nobody ever answered was, what are the formal relationships between these underspecification formalisms? Are these formalisms equivalent in any sense? And if they're not equivalent, is there at least some useful fragment of either the representation languages or of natural language on which they are equivalent? Yeah. So if we had a fragment of the underspecification language, of the formal language, which allows us to give an equivalence result, and we could show that every graph we ever need as an unspecified representation falls into this fragment, that would be useful enough. Yeah? So because it would mean, for all practical purposes, this wouldn't, hurt us. So these are all questions that, anybody answered, and but they're useful. They're important questions. It's theoretically interesting anyway, because what's the point of inventing the n+1st, formalism if there are already lots around? And, just to clarify the theoretical landscape, it's interesting. But there's also a practical aspect. And one of them is that for unspecified descriptions in minimal recursion semantics, there exist these large-scale HPSG grammars which parse, for example, English sentences and then give you unspecified descriptions in MRS. And then on the other hand, we've done a lot of work on actually solving dominance graphs. So from a graph, enumerate all the trees that are actually described by this tree. So we have more efficient solvers than they or anybody else has. And so it would be really interesting if we could clarify the relationship between MRS and dominance graphs, because that would mean that we get access to their grammars and they get access to our solvers. Yeah? So that's why in this talk I'm going to forget about all this, and I'm going to show you that you can, on useful fragments, encode MRS into dominance graphs, and you can get an equivalence between dominance graphs and another popular unspecification formalism, which is called whole semantics. Okay, so that's the goal of the rest of the talk. In order to do that, I'm going to give you the briefest possible introduction to MRS. Yes?
Sure. I'm just curious about
Yes.
the other formalisms, since I don't know any of them.
Yeah.
Is your guess that they're more powerful or less powerful?
In some cases, it's not even easy to say, because so things like MRS and UDIT, have very, aren't really, defined as cleanly as you'd want them to be, to actually, talk about expressive power. So that's one problem. Then this one is more expressive, because it's basically the first order language. I mean, we say, if you look at the logical language, we allow only conjunctions of our atoms, and he has, the full first order language. It's more expressive, but it also means, of course, that, it's much harder to do any computation with this. This is an older, perhaps the first ever unspecification formalism, and I don't know, it's a bit different from the others, and it's a good question whether this is more or less expressive. Yeah, and this is a super language of that. Yeah? So this is, this is a trivial inclusion arrow here. Yeah? So okay, so MRS in a nutshell, in our cleaner reconstruction. What you can do here is that again, the unspecified descriptions, you can write them down. You can see them as graphs if you like. And then what you have to do is that you have to configure the nodes of this graph into a tree in such a way that the dominance edges are respected, so not embed, but now configure. You must not have more in the tree than you had in the description. And there's an additional constraint which says that all holes must be plugged. I'll show you on the next slide what this means. And also, here this is more lenient in a sense, namely a node of the tree can have more than one label. So in our case, every node in the tree has exactly one label. In this case, a node can have at least one, as many as you like. So the way they would write something like every student reads a book is like this. So this looks very similar to what I showed you earlier. It has again the red and green and blue stuff here, and some dominance edges here, but now they go from the roots of these fragments to the root of this blue fragment, where we had them going out of. So these are called holes. These nodes without labels are holes, and one of the constraints in MRS is that you have to find something for each hole. Yeah? So no hole must be left empty. So this means if you try to arrange these nodes here into a tree, you have exactly two possibilities, namely the two ones you want. And that's not completely obvious at first sight, because if this if this fragment has to be somewhere below this root, it could be either below the left-hand child or below the right-hand child. Yeah. But the variant where it's below the left-hand child is not possible because then the right-hand child would remain unplugged. There's nothing that you could put in there possibly. So that's why by this sort of indirection, this has to be below the right-hand child, and that's why you get the correct release. Okay? You see already that this looks very, very similar to the graph we had earlier. And indeed, so this is now a slight change in the graphical notation. This is basically a representation of what you would get from the English resource grammar as output. But the difference are really minor, so it just says no more colors and things like that. Okay. So basically, what you can do here is that you translate an MRS graph into a dominance graph in a very simple way, in which you basically say, okay, I have this dominance edge down here. It starts at the root. That's not allowed in a dominance graph. I have to put it either to the left-hand child or the right-hand child. I already know something for the left-hand child, so I move it to the right-hand child, yeah? And then you end up with this. So by this kind of very simple post-processing step, you transform a well-formed MRS description to a well-formed dominance graph. And indeed, in this case, in this example, it works perfectly. This here has two solutions, and this here has two configurations. So it all works. And the good news is indeed that you can prove that if you have this kind of encoding, the solutions of the MRS description correspond one-to-one to configurations of the dominance graph. Yeah, that's good news on the one hand, because it's the first ever time that anybody proved a formal relationship between two underspecification formalisms. On the other hand, it's only partially good news because all the algorithms we have for dominance graphs don't compute configurations; they compute solutions. So these solutions are not actually solutions, but solved forms which represent sets of solutions. This is not the standard notion of satisfiability or solvability or so that we assume in a dominance graph. And you can actually make very small examples where you can see the difference. So if you look at this unspecified description here, this is a graph. You don't have to do anything to transform it into a nice dominance graph. But now if you try to solve this as an MRS description, it says, okay, here's one hole, and I have to plug it with both G and B. So it says, okay, I plug it with both G and B. But this is, of course, illegal in a dominance graph because now we have a tree node with two different labels. On the other hand, we say, okay, this node has to dominate a G and a B. I have to find some solution for this in which this is possible. So we say, okay, no problem. I invent something that has a branching, and I put the G as the left-hand child and the B as the right-hand child. So of course it's solvable, but of course this is not a solution of the MRS description because it has this green stuff in the middle, which this didn't mention, and this is not a solution of what we had, because it has this double labeling. So you see here's a mismatch. This means, strictly speaking, that the translation is not completely correct. And why is that? So the crucial case here is that the graphs, these underspecified descriptions on the left-hand side, had subgraphs of this kind where one node has two outgoing dominance edges. Yeah? So if you imagine that you never had nodes like this, you wouldn't end up with this ugly situation that you have one hole that you have to plug with two different things. Yeah? So this is really the crucial problem in these graphs. And now you have two different questions here. A, can you actually characterize a fragment that in some sense excludes this kind of subgraph, and that makes the encoding correct? And B, is this fragment big enough for everything you need in natural language? Okay? For scope and specification. How much time do I have? Okay, a little time. Okay, and the condition is the following thing. So we say that a dominance graph is hypernormally connected if every pair of nodes in this graph is connected by a simple hypernormal path. A hypernormal path is an undirected path in the graph, so it can use edges in either direction, an undirected path that never uses two adjacent dominance edges that come out of the same leaf. I'll show you examples here. And then, so it has to be hypernormal and it has to be simple. Simple just means it uses every node only once. Okay, so what's a hypernormal path? Here's an example of something that's not a hypernormal path. So this, if you take this path from A to B, it's an undirected path, so I can go up and down. And it's not hypernormal because I've gone into this leaf with a dominance edge and I've gone out again with another dominance edge. Okay, so that's why this is not hypernormal, this path. On the other hand, in this graph, I can walk from here to here by a hypernormal path, which goes up, down, yes? And it also uses two dominance edges. Perhaps this is a bit difficult to read because these look almost, so these are dominance edges and these are solid edges here. So it does use two dominance edges one after the other, but it goes into this node with a dominance edge and then out of this, so it goes down and then up with dominance edges. That's allowed in a hypernormal path. What's not allowed is to go up and then down. Okay? So we say that if every pair of nodes in a graph is connected by a simple hypernormal path, then the dominance graph is hypernormally connected. So this is not a hypernormally connected dominance graph because there's no, the only path from here to here is not hypernormal. There's a pair of nodes which is not connected by a hypernormal path. Whereas this graph here is indeed hypernormally connected. And this is despite the fact that it contains a node that has two outgoing dominance edges. Yeah, because, you know, I mean, I can still walk from here to here, for example. I mean, if I walked up and down, then of course it's not a hypernormal path, but there is a hypernormal path which goes down here and then up here again. So this is a hypernormally connected dominance graph, or a net. We call net is just a short word for hypernormally connected dominance graph. Okay? And now the really nice thing about nets is you can prove that you can define nets also on MRS and whole semantics. You can prove that if your MRS description is a net, then then there's no difference between so the basic lemma is that on hypernormally connected dominance graphs there's no difference between configurations and solutions. Whenever you have a solution, you also have a configuration that has no extra material. So that's why on all nets you know that there's a one-to-one correspondence between the MRS and the translation is correct from MRS to dominance graphs. And if you take a very similar translation from whole semantics to dominance graphs, and you restrict yourself to nets, then this mapping works and the reverse mapping also works. Yeah? So there's an equivalence between the net fragment, the hypernormally connected fragment of whole semantics, and the hypernormally connected fragment of dominance graphs. Okay? So what I've just said is these translations are in general incorrect, and that's, you know, because there are fundamental differences between the way that dominance looks at the world. You can add more stuff, and MRS works. You have to plug everything, and you can label things with more than one label. But if you restrict yourself to the hypernormally connected fragments, you can prove that the translations do become correct. Yeah? So now the really big question that remains here is, are all graphs that we need in scope underspecification hypernormally connected, yes or no? If you just take a small fragment of English, a small grammar, I mean, we've done this for a grammar with 15 rules or something, context-free grammar with 15 rules. I mean, just to see, you know, if it works on a small scale, you can actually prove this. So you take the grammar and you prove everything that this grammar produces is actually hypernormally connected. If you want to check this on a larger scale, of course it's infeasible to take a big grammar and at least, I mean, we have some ideas, perhaps it's possible, but, you know, it's a bit, you know, not so easy to take a large-scale grammar that somebody else wrote and then check if everything that it can possibly compute as an unspecified description is hypernormally connected. But what you can do is to do an empirical evaluation. And the setup for this is to say, we hope, or our claim is the following hypothesis. If you take any sentence of English and you run it through a parser, I mean, of course, this is grammar specific and everything, but I mean, you get good unspecified semantic representations out of it. You do end up with nets. Yeah? So that's we call this the net hypothesis. And to check whether it's true, we've done the following. We've taken the Redwood's tree bank. This is, I think, a part of the verbal corpus with HBSG parsers as annotations. This has a bit over 6,000 sentences. Then we took the English resource grammar and parsed, and computed the unspecified descriptions for each of these sentences, for each of these parsers. And then you get this green rectangle of unspecified descriptions in MRS. And then it turns out 83% of these are nets, are hypernormally connected, and 17% are not nets. But let's have a closer look at these. So here's one example, and there's a systematic, our impression is that they're systematically incomplete in the following sense. If you have a sentence like a cafeteria and a sauna are available, it has two equivalent readings because there's, it doesn't make a difference which of these two existential takes wide scope. The ERG would compute an unspecified, in the version we tried, computes an unspecified description that looks something like this. You have these two quantifiers, a cafeteria and a sauna, and then the variables x and y are used, are combined into this sort of plural object e. And this E is used in the predicate available. So this says E is available, and E is the combination of X and Y. This is not hypernormally connected, because there's no way to walk from something here to something there by a hypernormal path. But if you look at the solutions of this as an MRS description, you get all sorts of nonsense, where you have, E is available, and you haven't even said what E is. So conceptually, this end of EXY is something like a quantifier, which binds this variable E, and then the variable E is used over here. Okay. So really, what we should do, of course, a variable use should be in the scope of the quantifier that introduces it. So we really should have this additional dominance edge here that says yes, and also this available of E is in the scope of the end of EXY. Yeah, so this is, all of this except for this edge is, is originally the constraint that comes from the grammar. And this additional edge is an edge you need to introduce to, restrict it to exactly those two readings that you would, two equivalent readings that you would actually expect for this graph. Yeah? And if you do this, it becomes a net. Yeah? So now if you want to walk from this right-hand bubble to the left-hand bubble, you can just walk up to this dominance edge, and then you're home. Yeah? So you have a hypernormal connection between everything. Yeah? More generally, our claim is that although it turned out that 17% of the grammar of the grammar outputs from the Redwood tree bank are not nets, those 17% are systematically incomplete. So there are dominances like this missing in it. Yeah? And if you add them, then you actually do get only nets. Now we haven't tried this, we haven't looked at the 1,000 sentences that come out there, but it's something we'd like to do in the future. All the examples we've looked at, quite a few, all had, basically this form where, you had missing edges. Okay? So now let's harvest. So what we have now is we have equivalence results for the hypernormally connected fragments of dominance graphs, MRS, and whole semantics. And we have, let's say, at least the strong, well-founded belief that most or all relevant unspecified descriptions are indeed hypernormally connected. And now, what do we get from that? So the first thing is, this is the picture I had earlier. Two unconnected words. So now we have a translation from MRS into dominance graphs for the hypernormally connected fragments. So we get large-scale grammars that give us dominance graphs. They get efficient solvers for MRS descriptions, and that makes a big difference for them. For us, of course, we are really happy about this, because we don't have to write the grammars ourselves, and it's also really good for them, because here's a comparison of the runtimes for algorithms for actually at some point you do want to enumerate all the readings that are left over. Here's a comparison of the runtimes for an algorithm that does that, that enumerates all the solutions of all the configurations of a graph. On the x scale, you have the size of the graph, number of nodes. On the y scale, you have runtime in milliseconds. This is the logarithmic scale. Here's the graph for our solver. Here's the graph for the standard solver for MRS. And you see that it starts with a factor of 50 for very small constraints, for very small graphs, and it ends up with a factor of 500 for a bit like, these are still not terribly big sentences here. Could go on further down here. And you see that the factor will just grow and grow. That's one thing, and the other thing is that these error brackets here between the maximum and the minimum runtime for graphs of this size is much smaller for us than for them. Yeah, it looks very similar, but you remember that this is the logarithmic scale. Yeah? So this is a much wider distribution here than here. So this is much more predictable than what they have. Okay. And there are good reasons for this. Good. So that's number one. Number two is if you believe in the net hypothesis, if it turned, that is something that we could convince people of, it would be really useful for debugging large grammars, because when you develop a large grammar, of course, you have the problem that, when you touch, one part, there may be interdependencies that, cause effects on, that you didn't really expect. And it's perhaps not so easy to verify that the semantic output you get from such a grammar is good. Yeah? So if it's true that that every unspecified description structurally has to be a net, then the presence of non-nets in your semantic output could be a warning sign that there's something wrong with the semantics construction at that place. So perhaps you want to look at your semantics component in a bit more detail for the things that happen for this problematic sentence. And then finally, this work also contributes to finding out what you actually need to be able to say in an unspecified description. So if you have different unspecification formalisms, they use different atomic statements to talk about formulas. So we only say, here's labeling, so this node, there has to be a node that has this label, it has to have these children, and there has to be dominance, and that's all we can say. In MRS, you can say a few more things. There's a restricted form of dominance that says there has to be dominance, but everything that comes between the two ends of the dominance edge has to be a quantifier. And now, as a side product of our evaluation, we did get, the original source of MRS graphs and use it, namely the English source grammar, and it turned out that this never made a difference. Yeah, so we checked all the outputs, and it never makes a difference whether you have on the corpus whether you have equality up to quantifiers or just plain dominance. And then also the ability that you can label the same node with multiple labels is never necessary for nets. You can prove this. Yeah? So this is you can precompile the ability to have multiple labelings into complex, just use complex labels in the beginning, and then you don't have to worry about this anymore when you work with the graph. So it turns out that yes, you can do things with MRS that you cannot do with dominance graphs, but at least on the examples that we checked it for, those were not needed by the very same people, not used by the same people who actually invented the formalism. Okay. So here's a conclusion. The point about underspecification is that you want to be able to deal with particular scope ambiguities by delaying the enumeration of the readings. You'd like to do things to the unspecified description first before you actually enumerate the readings. There are lots of different underspecification formalisms, and the question is, are they different or are they all the same? There are differences, but as I've shown you, there are relevant fragments, namely the hypernormally connected fragments, the fragment of nets, on which dominance graphs and MRS and whole semantics all say the same things and can be converted into each other. And this is theoretically nice, and it's useful because it allows us to share resources between different underspecification formalisms. Now, it would be interesting to extend this to other underspecification formalisms. One thing that's also interesting is to develop an efficient test for hypernormal connectedness that says, is this graph actually hypernormally connected, yes or no? That's not completely trivial because the relation of two nodes being hypernormally connected is not transitive, so you cannot use just standard connectedness algorithms. But we have ideas, so we're going to implement them and rerun the evaluation. There's also a new version of the grammar, and it's going to be interesting to see what comes out there. Then I'd like to go over every single instance from the tree bank that's not a net and see if this claim actually holds up, that everything that's not a net is incomplete. And then the basic take-home message from this whole thing, I think, is that there's not really any. I mean, underspecification has, on the formal level, on the level of how to actually write down the underspecified representations, matured to a point that we're beginning to understand how everything fits together. So things have grown apart for a bit, and now they're beginning to grow together again. So we can just take our pick of the things that are already there. But there's a lot of interesting stuff that's still to be done on underspecified descriptions, including to actually fulfill this promise that you can do something interesting with underspecified descriptions before enumerating the readings. So I think that's the really big cornerstone that still has to be satisfied. There's some work on this, and I'd be happy to tell you some about it. But it all doesn't really work really well yet. Yeah? So also combination with statistical things. There's a lot of interesting stuff that still needs to be done, and I think my opinion is we should just get on with doing this instead of inventing new formalisms all over the place. Thank you.
So quantifier scope is said to be close-bounded. So if you say something like a student said that John read every book, you don't get the wide scope of every book. So does your underspecification account for that, or would it just give you ambiguity where there isn't?
You can do that in the syntax semantics interface. You can at that point just add a dominance edge from the argument position of the verb to every book or what it was, and then it would enforce the verb to take scope over the every book. That's no problem.
You have to enforce some extrinsic restriction.
Yeah, and that is being done on the large scale in the grammars.
So when you talk about getting on with underspecification work, are you talking about the syntax semantics interface, or are you talking about reasoning with the underspecified representation?
There are certainly interesting things that can be done on the level of the syntax semantics interface. So I've just, at Penn, there's now this initiative to put underspecified semantics into the extract grammar. And they have different opinions from the people who wrote the English source grammar on what scope readings a sentence actually has. So there are these classical Hobbes and Schieber sentences with every researcher of a company saw most samples, which they claim has 5 readings, and which the extract people say, yes, but it only has 5 readings because a company is an indefinite and not a real quantifier, and if it were a real quantifier, the sentence would only have 4 readings and not 5. Yeah? So I personally find it tricky to get to an opinion there, but there's certainly things that can be done in the syntax semantics interface that are interesting work. So that's that. On the other hand, for me, what I find really interesting is to do inferences on the underspecified description, so you can actually say, yes, okay, the underspecified description says there are 65,000 readings, yeah, but there aren't really 65,000 readings. All those, most of those, if you look at the graph that comes from this, are things like definite article. Yeah? So if you have definite ambiguities, it's not a real. It's completely spurious. Yeah. So you would like to be able to sort of cook this down and then say, okay, but it looks like at first glance the grammar said it had 65,000 readings, but 64,000 are all completely equivalent. So I just need one representative, and I can forget about the other 64,000 ones. There has been a little work on doing this stuff with equivalent readings by a guy in Portugal that does something, but he didn't have any results, of completeness that said, this is actually the kind of spurious ambiguity that I can get rid of. Then there's readings that you can discount because they contradict external knowledge sources. So if you have, every boy eats a cookie, for example, it's theoretically has two readings, but one of them is, quite disgusting and implausible, and you'd like to be able to use some information about cookie eating in order to get to throw away the one that's implausible or impossible, or in a certain sense, I think impossible perhaps in this case. I have tried to do that in my thesis, and it works somewhat, but not really well. So I have some ideas on how to continue that, but that's tricky too. One thing that works is you can use information about anaphoric references. So if you have every man loves a woman, her name is Mary, so you have an anaphoric reference from her name from pronoun her to a woman. You only get one reading too from the first sentence. And you can explain that with European theories of dynamic semantics that say, okay, it has to be accessible for the anaphoric reference. And that's something we've done a few years ago, and that works pretty well. Yeah? So that's at this point one thing I'd like to be able to do, and that's what I mean here when I say let's get on with underspecification work. And then there's of course the whole question: can you use statistical information? Because perhaps you have preferences for understanding scope ambiguities. And I believe the things we've done here are, also algorithms are a platform in which you can do this. There are, we have, ideas on how to do this. We have implemented an algorithm with a star search for an optimal solution. The problem here is that it's really tricky to get data to actually train a probabilistic model on. Because, we have experimented with this, so we have tried to annotate a corpus with, scope information, and after 150 sentences we stopped, because it was just so incredibly much work to just, agree on the scope reading that you actually have in mind. You do find examples, in corpora, lots and lots of examples, but it's almost, it's so closely linked to other kinds of ambiguity, like type token ambiguity, for example. Yeah, so we had some really nice examples where if you take one reading of the type, if you look at it as a type, then it has wide scope. If you look at it as a token, it has narrow scope, and in those cases you get horrible inter-annotator agreement. So that's why we shelved this project of of actually annotating this stuff. If somebody has ideas on how to do this, I'd be extremely happy to discuss them. We have ideas how to do it formally if we got the probabilities from somewhere, but we don't have them. Yeah? So that's the kind of state of the art here. And then you can continue thinking about this in a way that you say people don't really commit. If you look at the sentence like with the every politician can fool most voters, etc. I don't commit on a single scope reading when I look at that sentence. Yeah? And the reason for that is that I don't have to. I can get some information from from my present purpose from that sentence. And if somebody forced me to actually look at this, if I'm a lawyer or so, and I have to, actually, sue somebody and get, ammunition from this sentence, then I would actually go to this perhaps and say, oh yes, he meant, most different voters for every politician. So there's something that scope ambiguities are an interesting kind of ambiguity in the sense that they're, I think, generally only very partially resolved. And only if you really have to, you start resolving them. So there's something also about the depth in which you go in your search for a solution and at which level of underspecification you stop, how far you actually go with this ambiguation. So that's the kind of work I mean when I say let's get on with it.
So what is it about the semantics or the structure of language which would make it the case that all of the graphs that are in fact not incomplete but generated by a parser from actual sentences are nets?
That's a very good question. I don't have a complete answer to that, but I can give you an idea perhaps. So, if you look at, imagine that this is every student a book and read. Okay, so this is the same structure that you have these two different quantifiers dominating the matrix. So, you do have these two are basically tied down by these two dominances here because this is a verb that takes these two things as arguments. Yeah, and this contains variables that these quantifiers bind. Yeah, if you continue, if you have these three quantifier sentence like every researcher of a company saw most books or so, then you would have something like every researcher, a company, and you presumably analyze this by having some sort of belonging to a relationship down here that connects the researchers and the companies. Okay, so the intuition is that quantifiers don't really float around completely freely, but the core meaning of the sentence is what's down here in the verb, for example, and then the quantifiers float around above it, and they're connected to the verb because the quantifiers are only there because the verb needs its variables bound. Yeah? So that's why I think that this sort of two things that dominate something together, this is a very fundamental structure, I think, in underspecified descriptions. And nets are basically just a way to say what exactly does it mean that everything is tied down properly? So that's my intuition about this, but it's not a complete answer, of course, about the nature of, scopes.
So in fact, with the incomplete graphs that you talked about coming out of the parser, did the spurious solutions actually not have interpretations as formulae?
Yeah, it depends on how you look at it. So these are two of them. Okay. So if you forget about the available for a moment, so imagine first that the available is down here where it belongs. Yeah? Then it says there is a cafeteria X and there's a sauna Y and there's something, a plural object E, which is the combination of X and Y, and it's available. Yeah? So this makes perfect sense. Now, if you look at this, so this is a case where MRS has this multiple labeling of one node, and this is then interpreted as conjunction by them. So this says E is available, and also there's a cafeteria, and Y there's something, an unbound variable E is available. And also there's an X and a Y, there are cafeterias and saunas, and there's this E which is Y. So you could imagine that perhaps you have a global binder for this E or so. You imagine there's an exists E on top of everything else, and then sort of you get something that kind of makes sense, but there's not really any point to allow these extra spurious things. I mean, this available can just go anywhere. Yeah. So I mean, there's no restriction whatsoever. Which node this available E could map to. So if you touch this a bit, you can make them into well-formed semantic representations. But it's really, I mean, this is clearly not intended to be just freely combinable with everything.
Well, what this reminds me of is if you take a free group modulo some commutativity equations, so you allow some things, some things this order and that order are the same thing. You put them in the same equivalence class.
Mm-hmm.
Other things can't move past one another. Mm-hmm. I mean that's done with strings rather than with trees. Mm-hmm. But maybe the same idea applies.
I would find that a very interesting idea to look into in the context of making of getting rid of spurious readings, where you have actual imagine this is tied down properly and it's down here. You still have the situation that you have a cafeteria and a sauna, and you have two different orderings, you know, of the
Yes, that's right. That's what I was looking at in the
of the existentials, and they're completely equivalent. That's an interesting idea. Yeah. So I mean, one problem with all this stuff is that you don't really. It's sort of a non-local kind of influence, because you have to look at. This is an interesting question. Yeah. So I've done something like this with rewriting, but if we can do it with 3 groups, let's try it. Yeah.
Okay, well, let's thank our speaker again. So for once, we actually have a rational order of speech and meetings. Alexander wasn't here today, but he'll be back again on Thursday, and you can sign up with Sue if you want to talk to him. He really has very broad interests that span the Atlantic Divide.
Thursday and Friday.